Hello and welcome back to Calculus 1 section 3.2. We are talking about relationship between the function and the derivative. So we already saw that the derivative is a function itself which generates or computes the slopes of the tangent line to the original function f of x. And now we want to take a look at the connection between the original function f of x and the derivative graphically. So what I want to do is to represent a function first as, let's say, a 45 increase from -4 on x-axis to +4 on y-axis. Then I want to have a flat piece up to 3 constant, and then I want to have a 45 degree downwards towards 7. So I have this function f of x, and I want it to end at 7. So the black one is f of x. So how does the derivative look like? Well, I'm going to say something that I haven't said before. And the derivative measures the change. If you look at the derivative definition, it came from slope formula, and the slope formula measures the change. So it is the change in y divided by change in x. So the derivative inherits all of those properties because that's the formula, it just has the limit attached to it. So derivative measures the change. Now, as you are looking at the graph of from -4 to 0, interval, -4 to 0, as you are looking at that interval, you see that the function is changing with a constant rate of 1. 1 square up, 1 to the right. 1 square up, 1 to the right. So the slope of that change is 1, and we know that the derivative is 1. So this is f prime. The red line is f prime, and it's just constant because we have a steady change in a positive direction. So 1 square up, 1 square to the right, 1 square up, 1 square to the right. Now what's happening 0 to 3? Is there a change there? No change. So if there is no change, what is the derivative? 0. So for this next piece on the interval 0 to 3, there is no change because the line is not increasing or decreasing, and because there is no change, the derivative is 0. Derivative measures the change. If there is no change, then derivative is 0. And now we have a negative change. If you look from 3 to 7, the change is still 1 unit, but in the negative fashion because because the function is decreasing. So you have to go 1 unit down, 1 unit to the right, 1 unit down, 1 unit to the right. And that introduces the negative slope, which means the derivative is -1, right here. So I'm going to point one more time over here on the left part of the graph. We have increasing function. And because it's increasing at a steady rate, the derivative is +1 because your Slope of the function is 1 over 1. Remember that derivative is the slope, right? And then we are moving into the next part, which is this part here, that has no change. And because there is no change there, the derivative must be 0. Derivative measures the change, and there was no change on the interval 0 to 3. Finally, we are getting here, and this part is where we have a negative change. The slope is negative because we are going down and 1 over and down and 1 over. So it's a -1 constant change. So now we have our first graphical connection between the two. Now the next step in this evolution is to take a look at some random function. And for this function, let's go with something like this. So it had these few waves and going up and down, and then ends up being a flat piece going off to infinity. So that's flat. Uh-oh. So this piece over here is flat. So that's f of x black, right? Original function. And now I'm going to write the derivative, which will be red. The derivative measures the change, and at any point on the graph that we place, anywhere, where you place the point, you are able to find the slope of the tangent line. Slope of the tangent line shows the increase or decrease. It shows positive or negative derivative, right? What is happening at these peak points? Everything except the first one. I'm going to actually erase this one. There we go. So what's happening at these peak points? Tangent lines are horizontal. So what is the derivative at those points? Yes? 0. Very good. So the derivative must pass through the x-axis. Maybe you want to write this as a sentence. The derivative must pass through the x-axis wherever the function has a min or a max. Derivative must pass through the x-axis wherever the function has either a min or a max. Now I told you why. Yes?
The derivative has to pass through the x-axis with the min or max, which we said.
On the original function, yeah. Original function. See how this is a maximum?
Yeah, but that's not passing the x-axis.
No, but the derivative will. I didn't draw.
The
Derivative will be the red line. I haven't done anything yet there. Okay, so so this is at first a little bit counterintuitive, but just keep in mind when function is increasing or decreasing, derivative gets to be positive or negative, which means below or above x-axis. So one more time. If f of x is increasing, f prime of x is positive. If original function f of s is decreasing, f prime of x is negative. If f of x has min or a max, that's when the function goes through the x-axis. So now look at this. You should really drop your pens and watch so it's not confusing. On this part of the line here, the function is increasing, which means that the derivative is positive. So derivative has to be above x-axis because the function is increasing, and increasing function means derivative is positive, above x-axis. Now on this part here, the function is decreasing, next partition, function is decreasing, and then will be increasing again. So look, it's so natural to expect for this part to be on the negative side, because look, first the progression, right? And then also the decreasing function is a negative derivative. Negative derivative means values are less than, right, on the negative numbers here. And then as soon as it hits the minimum there, it's going to be increasing again, so it's going to be positive. Increase means positive. Look, increase, positive. This increase, another positive piece, and then we'll go negative again. So the next piece is going to look like this, because that's increasing part, it better be positive. And then from max to another min, it's decreasing, it's going to be another negative part here. Now we don't know how high or how low we get to draw, because we don't have the exact function. This peak could be there, right? This peak could be anywhere on that line. Now we are going to go up to this point here. It's increasing, so it's going to increase. After this, it's going to increase, and then drop and be zero forever, because there is no change on that flat part. Whether or not, that's it. We still have to say just the vertical asymptotes are preserved. So whenever you have the vertical asymptote, we'll do one more example for that. So looking at this, what do I have? I have the function is increasing, derivative is positive, function is decreasing, derivative is negative, function is increasing, positive, function is decreasing, negative, function is increasing, positive, and then function is constant, it's 0. One more example that will verify one more thing. So we said earlier, if the function is 1 over x, if the function is 1 over x, the derivative of that function was negative 1 over x squared. Very good. Now we know how both of these functions look like because they're basic functions. But we can show that 1 over x will produce negative 1 over x squared graph, and make sure vertical asymptotes locations are preserved between the function and derivative. So you know you have a vertical asymptote at 0, you still have a vertical asymptote at 0. So now what's happening here? No min, no max, that means it's not crossing the x-axis, right? Because when you have min or a max, you have the horizontal tangent line. Horizontal tangent line means slope is 0, and that's why derivative crosses the x-axis at that point, because slope was 0. But we don't have min and max now, and because we don't have min and max, we don't get to put any x-intercepts for derivative. But what do I have? I have a decreasing function. And when I have a decreasing function, and the derivative still has to have the same asymptote, the piece for the derivative must look like this. It must. Because it has to follow the asymptote. It can't cross the x-axis. There is no min or max. And it has to follow the same vertical asymptote. So that piece must look like that. And then you go and look at the other piece on the other side, and that's decreasing as well. So the other side looks like this as well. So that's my f prime of x. The black lines are 1 over x, and the red lines are the derivative, which is negative 1 over x squared. Now, if you remember your pre-calculus, well, you would remember that 1 over x squared graphs this way, which means that negative 1 over x squared has to flip and will graph that way, which is exactly what we have for the red line. What negative sign does is just flips it on the x-axis. And that's exactly what we got. All of the mathematics always links and clicks right in the spot. No exceptions anywhere, in any case. So that's the graphical connection between the graphs, and we will see. So now we know the tangent line, we know how the graphs of both of these work together. So that's the end of this lecture. We'll talk more about derivatives, obviously, next class. We'll have the review. Let me just shut this off by stream.